Well, in this video, we are going to prove that the set of 2 by 2 matrices with real entries is a ring under multiplication and addition. So M sub 2 of R is the set of 2 by 2 matrices. So in other words, the elements in this set are matrices. And so matrices have entries A, B, C, and D. It is worth noting that we do not have that condition about the determinant being non-zero here. That was the defining condition for what we call the general linear group. That's a proper subset of these matrices. So there are more matrices here. Here we're allowing examples where the determinant is 0. And there are two operations on these matrices we can do. You can add matrices. And how do you add matrices? Well, you add each of the corresponding entries. So the top left corner is the sum of the entries in the top left corners. The top right corner is the sum of the entries in the top right corner. The bottom left corner is the sum of the entries in the bottom left corners. And the bottom right corner is the sum of the entries in the bottom right corner. In general, the ijth entry in the sum of two matrices is the sum of the ijth entry in the individual matrices. And multiplication is as we had it before. The ijth entry in the product of two matrices is this summation of aik times bkj, as k goes from 1 to n. The idea is that you multiply the entries in the ith row of the first matrix times the entries in the jth column of the second matrix, which means, of course, you're taking the dot product of those corresponding vectors. So the dot product of the ith row vector times the jth column vector. And so that's what I have written here in the case of the 2 by 2 matrix. And the claim in general is that if you take n by n matrices whose entries are in any ring with these definitions, then you get a ring. Because note, as long as the entries are from a ring, you can talk about adding the entries, and you can talk about multiplying and adding entries. Of course, for the sake of this video, I'm only going to focus on real numbers and n equals 2. So 2 by 2 matrices with real entries. So our claim is that 2 by 2 matrices form a ring. What does this mean? Well, first, this means that when you look at addition, you get an abelian group. Second, it means that when you look at multiplication, you get associativity. So the product of any three matrices is the same regardless of where you put the parentheses. Worth pointing out, we know for a fact that matrix multiplication is not necessarily commutative. Finally, the new property is the distributive property. For any three matrices, A times B plus C is equal to AB plus AC, and A plus B times C is equal to AC plus BC. If you go back to your linear algebra textbook, these properties of matrices are usually listed in the textbook. So the fact that it's a ring is already something you've seen before, just without the terminology. So step 1, we have to prove that you have an abelian group under addition. Worth reminding ourselves that that means that we need to prove associativity of addition, and we need to find an identity element, which we call 0. And we need to find inverses, additive inverses. So let's start with associativity. Let A, B, and C be 2 by 2 matrices. I'm going to use this subscript notation. Let's compute the ijth entry of this triple sum. By definition of addition, it is the sum of the ijth entry of a plus b with the ijth entry of c. By definition of addition, the ijth entry of a plus b is the sum of the ijth entries of a and b. So we've gone from an entry in a matrix to the sum of entries from two different matrices to the sum of entries from three different matrices. So these are just three numbers now. But addition for real numbers is associative, so we can move the parentheses over. And now we can work backwards. This is the sum of the ijth entry of two matrices, so it's the ijth entry of b plus c. Likewise, we're adding the ijth entry of a to the ijth entry of b plus c. So this is equal to the ijth entry of this triple sum. And so for all I and j, we have the ijth entry of a plus b parentheses plus c is equal to a plus parentheses b plus c. But that's the definition of equality for matrices. So these two matrices are actually the same, and therefore we have associativity. Of course, to be an abelian group, you also have to have commutativity. So now you take two matrices. The ijth entry of a plus b is a sub ij plus b sub ij. Addition of real numbers is commutative, so we can change the order. And then that's just the ijth entry of b plus a. So these two matrices have the same entries, therefore they're the same matrix. And so addition is commutative. Finally, we need the identity element and the inverses. It turns out the identity element is going to be the matrix whose entries are all 0. And the negative is this one. It's worth pointing out. Negative A, B, C, D is just negative A, negative B, negative C, negative D. So using summation or index notation, you can check that a plus 0 sub ij is the sum of these two matrices. Since 0 sub ij is 0, adding any number to 0 gives you that number back. So you get a plus 0 is a. Similarly, if I add this matrix to this negative matrix, I look at the ijth entry, that's the sum of the ijth entries. By definition, the ijth entry of negative a is negative aij. These two numbers cancel and I get 0. So the entries in this matrix are all 0. It's the 0 matrix. This is actually the negative. Seeing that argument a different way, if I add the 0 matrix to any other matrix, I'm just adding 0 to every entry. And that gives me the other matrix back. Likewise, if I add the negative of a matrix to itself, that's the same as these negative entries. Well, then I have a minus a, b minus b, c minus c, and d minus d. It's the all 0 matrix. So in the 2 by 2 case, you can actually write it down explicitly like this. The reason I don't do this for associativity And the other parts of the argument is because, well, then you're just dealing with 3 matrices, and okay, it's possible you could do it but it just takes a lot more time, and it's easier to use the index notation. And as you'll see, I have to use the index notation for proving distributivity. Or at the very least, that proof gets a lot harder. So congratulations, 2 by 2 matrices form a group under addition. This is actually, should not be that surprising. In linear algebra, you actually prove that this is a vector space. And so being a vector space already means it has to be an abelian group with respect to addition. So this is part of that proof, just the part where you ignore scalars. All right, so to be a ring, we have to do more work. We also have to show associativity with respect to multiplication. Here I'm going to punt a little bit to a previous video. Way back when we studied the general linear group, I pointed out that for 3 matrices, we had associativity. When you multiplied them together, that proof did not use determinants at all. So that same proof works for matrices even if their determinants are 0. So in particular, associativity still holds. So one can just go back and copy and paste that proof word for word, and it's the same argument. So matrix multiplication is associative. So the final step is the distributive laws. So take 3 matrices, show that A times B plus C is equal to AB plus AC. So finally we show that multiplication distributes over addition. Take your 3 matrices. Let's look at the ijth entry of A times B plus C. Well, by definition of matrix multiplication, this is this sum of the, so it's the dot product of the ith row of A and the jth column of B plus C. So sum as k goes from 1 to n, aik, something kj. So the kjth entry of B plus C. By definition of matrix addition, that's the sum of the kjth entries of B and C. Multiplication distributes over addition. So this expression can be replaced with aik bkj plus aik ckj. And then you're doing this addition, you can split the sum into 2 separate sums. Sum over the bkj's and sum over the ckj's. And then you look at this and you realize this is the ijth entry of A times B, and this second summation is the ijth entry of A times C. And I probably should have done at least one last step. That means you're looking at the ijth entry of this sum of 2 matrices. And so we see these 2 very ugly looking matrices have the same entries, therefore they're equal. So matrix multiplication does distribute over matrix addition. However, as we saw in a previous video, just because you're distributive over the left does not mean you're distributive on the right, so we actually do have to include the other proof. So here it is. It's essentially the same argument. So the good news is usually the proof looks similar, but you still have to include it because there's unfortunately no way around it because there are bad examples. So it's not guaranteed. Take 3 matrices, add the second 2 together, multiply by the first. Look at the ijth entry. By definition of multiplication, it's this summation over the ikth entry at the sum of the 2 matrices times the kjth entry of the third matrix. Then the rest of the proof looks just like on the previous step. You replace the sum of the two matrices with the sum of their entries. You apply the distributive law for real numbers. You rewrite a summation of two sums, well, a summation of binomials as the sum of two summations. Then you recognize that you're looking at two dot products here. And then this is just the ijth entry of b times a, and this is the ijth entry of ca. So this is really the ijth entry of the sum of the two matrices. And so you get the same distributive law. Thus, we see that the set of 2 by 2 matrices with real entries is in fact a ring. It is an abelian group with respect to addition, so you have associativity, commutativity, and additive identity, and additive inverses. And you have associativity with respect to multiplication, and we had multiplication distributes over addition. We had to do both distributive laws because it turns out in this case it is not a commutative ring. Because, for instance, if I take these two matrices and multiply them in this order, I get the matrix with the 2 in the upper left-hand corner. But if I multiply them in the other order, I get the all ones matrix. And since these two matrices are not the same, we see that A times B is not equal to B times A in general. There are some cases where it's true and some cases where it's not.